Hello everyone, today let's solve the problem number 104, maximum depth of the binary tree. So this is easy, right? So easy question. So here, what the question states, we are given the root of the binary tree. See here, we are given the root of the binary tree and we have to return its maximum depth, right? So here, let me come to the first example. See here, we have been given root of the binary tree and we have to return its maximum depth. Maximum depth is nothing but the number of nodes along the longest path. See, just give me a second here. One second. Yeah, the maximum depth is nothing but number of nodes along the longest path from the root node to the farthest leaf node. See here, we can consider this one directly connected or this one. This is the basically this one longest path from the root node to the farthest leaf node, right? So we need to return 0 if the tree is empty. If the tree doesn't consist of any value at all, then at that case we have to return 0. At that case we have to return 0. And here in this case it is 3, maximum depth 1 2 3, or you can consider this one as well, it doesn't matter, right? So here in this case the longest path from the root node to the farthest leaf node is 3, or the maximum depth is 3. So we need to return the value 3. Basically whenever we write the code, it will be 0 index. Just take care of this one. Whenever we start from the root node, whenever we write the code, usually it is from the 0. So we have to add +1, right? If we go with the recursion, right? So we have to add +1. Just keep this in mind, man. That's it, right? So this is it for the question. This is it for the question. Simple one, right? So here we have 1, null, and 2. So this will be like this basically. 1, this is null, and left part is null, and the second, this one will be 2. So the depth is here 2 itself, right? So this will be 1 and this will be 2. The maximum depth we have to return here in this case is 2, right? So this is it for the question. So I hope the question part is completely clear, man. Now let's discuss the, what do you think? So what do you call this one? Let's discuss the approach followed by the complexities and then let's write the code. So here first let's discuss the approach. So let's consider the same first example here. So here we will be going with the first thing I want to tell you is we will be going with a DFS approach. So we'll be going with a recursive DFS or the DFS. Just keep this in mind. We will be going with a recursive DFS. We'll be going with a recursive DFS. Just keep this in mind, right? So this is fine. Now let's come to the first example. Yeah, the approach that we'll be going with is recursive DFS that I have said clearly. And now let's consider the same first example here. We will start from root 3. We'll always start from the root node, right? So here we'll start from the root 3. Depth is 1. This depth is 1. Now we will go left. We have 9. So we are performing DFS right here, depth first search. So now we'll go to 9. This one I'm speaking of 9, right? So here there are no children for 9. So left depth is 2. Left depth is 2. Now what we'll do, we'll go right. We will go right. We'll go right. This one, right? So now we have the value 20. Basically, we have the value 20, right? So now for the 20 we have sub children 15 and 7, right? So we will go left first, 15, this one, right? So the leaf, right? So now the depth is 3 for this one. The depth is 3, and we will go this one, we'll explore 7 as well, this one. For the 20 we have two sub children here, right? So this is also 3 basically. This is 1, this is 2, 20 is nothing but 2 here. This one 3 3, right? So max of the left and right we will consider. So left it is 2, and max of right you can consider either this 3 or this 3 will consider, right? So here now we will go with max of left and right. So we are going with the DFS, right? Recursive DFS. So we will consider max of left and right. Max of left is nothing but 2 here. This is max of left, and this is max of right. Max of left is 2 and max of right is 3, right? So now we will consider maximum of 2 and 3, nothing but here in this case it is 3. In this case it is 3. So we will return the maximum depth, nothing but 3 we got. We will consider the max of 2 and 3, nothing but the 3. So here we got the output 3. We will return this one. So the output that we got here is 3, which is equivalent to the output that they have mentioned for the this one, that they have mentioned in the first example, right? So our approach works absolutely correct in this case. Now, as we are completely familiar with the approach, let's move on with the complexities part, right? So here, what will be the time complexity? The time complexity here would be big O of n. Why it is big O of n? Because we are going with the DFS, right? Means here, by making use of the DFS, we will be visiting each node exactly once. We'll be visiting each node exactly once. So the time complexity, overall time complexity would be big O of n. So what would be the space complexity? The space complexity we can consider big O of h rather than big O of n. So we know that the recursion stack depth goes up to big of n, right? So due to the recursion stack, it would be big of n. We can consider big of n as well, but it is better to consider h, because h is nothing but the height of the tree, and in the worst case we have to consider, or we will be considering the skewed tree. In the worst case, we'll be considering the skewed tree. So overall space complexity would be big of h here. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of h respectively, right? So I hope the complexities part is completely clear. Now, as we are completely familiar with the approach as well as the complexities, we are good to write the code. Let's start writing the code, right? So here, first step is, let's go with the base case. Means if the tree is empty, then the depth is 0. They have strictly mentioned in the question. So if the tree is empty, then we have to return 0, right? So nothing but depth will be 0. If we don't have any value, or if no node is present in the tree, then the depth we have to return as 0, right? So here, if we can write in this way, if root equals null, then we will return 0. This is fine. Next step is we have to recursively find the depth of the left subtree. This will be int left depth equals, so this one will be max depth of root dot left. This is fine. Next step would be we have to recursively find the depth of the right subtree. So this one will be right depth equals, so this one will be max depth of uh, root dot right. So this is fine. Hmm, yeah. The next step would be the depth of the current node is nothing but the max of left and right subtree, and also plus one, because the indexing, binary tree indexing starts from 0. We know this one, right? So we are starting with the node, it starts from 0. Basically we need from 1, right? So this has to be 1 index, so we will be going with a plus 1 for this one, right? So the depth of the current node is max of left and right. We have discussed this one in the approach. Same thing will be articulating in the form of code, and we'll be going with a plus 1 as the binary tree indexing is this one, 0 indexed, as it is 0 indexed, right? So basically what we will do here, let me go with return mat dot max of here left depth comma right depth. So here in this case, this is fine. This will be plus 1, right? So plus 1 we have to give whole plus 1, right? So this is fine. This is it for the code. Let me hit the run button. I hope this works, man. Let's see. Yeah, you can clearly see here the sample test cases are getting passed. So let me hit the submit button quickly. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct in this case, right? So the code works absolutely correct in this case. Now we are done with the code. We are done with the coding part, right? So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.